Jupiter's moon, Europa, has had a liquid water ocean for 4.5 billion years, longer than Earth's oldest surviving rocks, longer than the first evidence of life in our geological record, and the spacecraft is already on its way there right now. Subscribe. There's a new one every few days. White space. Let's take this slowly. There is a moment shortly after launch when a spacecraft crosses the orbit of Mars and enters the outer solar system for the first time. The instruments are quiet, the cameras are turned inward, storing energy, conserving heat. From here, the sun is already small enough to hold behind your thumb. It no longer fills the sky with warmth. It has become just another star, bright but distant, pulling at the spacecraft with gravity that grows weaker with every passing week. Ahead lies the largest gravitational presence in the solar system, a planet so vast that all the other worlds could fit inside it with room to spare. A world that generates more heat than it receives, that wraps itself in magnetic fields powerful enough to engulf the moon's entire orbit, that has orbited the sun more than 20 times since the first multicellular life appeared on Earth. What draws us to Jupiter is not merely its size, it is the growing suspicion supported by every mission we have sent there, that in the frozen moons orbiting this enormous world, something may already be alive. And that answering that question may be the most consequential scientific act our species ever undertakes. On August 5, 2011, the Juno spacecraft lifted off from Cape Canaveral aboard an Atlas V rocket. Its destination was Jupiter, some 2.8 billion kilometers away via the trajectory engineers had chosen, an elegant arc that looped back toward Earth for a gravitational assist in October 2013, borrowing momentum from our own planet to fling itself outward into the cold. During the cruise phase, Juno's scientific instruments were powered down to conserve energy. The spacecraft rotated at 2 revolutions per minute, a slow spin that stabilized its attitude and kept its 3 enormous solar panels, each stretching nearly 9 meters. Tracking the sun. By the time Juno reached Jupiter, those panels were receiving sunlight 25 times weaker than at Earth, and engineers had spent years optimizing every watt of power the mission consumed. Juno arrived at Jupiter on July 4, 2016. It fired its main engine for 35 minutes to slow itself by 542 meters per second, barely enough, at interplanetary speeds, but precisely enough to be captured. The spacecraft slipped into an elongated polar orbit and survived. The first full science pass came 53 days later, when Juno swept from high above the North Pole down through Jupiter's equatorial radiation belts, screaming past the cloud tops at over 200,000 kilometers per hour, saturating its instruments with data in a 6-hour window of closest approach before climbing back out into the relative safety of the outer orbit. This repeating pattern, 53 days of cruise, a few hours of intense science, 53 more days of cruise, defined the rhythm of Juno's primary mission. The radiation environment around Jupiter is the most punishing in the solar system. Jupiter's magnetic field traps high-energy electrons and protons in belts analogous to Earth's Van Allen belts, but orders of magnitude more intense. A human standing unshielded at Juno's closest approach altitude would receive a lethal radiation dose within seconds. The spacecraft's electronics were housed inside a titanium vault 180 kilograms in mass, designed to reduce the radiation dose by a factor of 800. Even so, mission planners expected the cumulative radiation damage to degrade Juno's instruments over time, and the spacecraft's operational life was defined partly by how long its systems could endure that punishment. Juno carried 9 scientific instruments, each targeting a different aspect of the planet's physics. A microwave radiometer, the instrument most unique to this mission, used 6 antennas operating at different frequencies to sense thermal emission from progressively deeper layers of the atmosphere. The longer the wavelength, the deeper the antenna could see, from the shallowest ammonia cloud layer to depths of 550 kilometers below the cloud tops, where pressure reaches roughly 100 atmospheres. By comparing emission at different frequencies, the instrument could map the temperature and composition of the atmosphere through its full vertical range, revealing the three-dimensional structure of features that are visible only at their tops from above. Magnetometers measured the strength and direction of Jupiter's magnetic field with a precision never before achieved, sampling continuously throughout each orbit. Two separate magnetometers were mounted at the end of one of Juno's solar panel booms, far from the spacecraft's own electrical systems, to minimize interference. The data they collected over multiple orbits allowed scientists to build a complete spherical harmonic model of Jupiter's field, the mathematical description of how the field varies across the planet's surface, with enough terms to capture its complex asymmetric structure. An ultraviolet spectrograph observed the polar auroras, which on Jupiter are produced by a combination of mechanisms absent on Earth. The direct precipitation of particles from the solar wind, the field-aligned currents driven by Io's plasma torus, and the breaking of co-rotating plasma at the outer edge of the magnetosphere, where particles cannot keep pace with Jupiter's 10-hour rotation. The auroras at Jupiter's poles are therefore permanent features, present regardless of solar activity, far brighter in absolute terms than anything produced at Earth, and shaped by a complex interplay of forces that planetary scientists are still disentangling. JunoCam, the visible light camera, was the mission's public face, a fixed focal length imager that took images during each close approach, returning pictures of swirling clouds, cyclonic systems, and the chaotic polar regions that had never been photographed at these resolutions before. What Juno found rewrote our understanding of the giant planet in several important respects. The interior of Jupiter had long been modeled as a relatively simple layered structure, a dense central core of rock and ice, perhaps 10 to 20 Earth masses, surrounded by a layer of metallic hydrogen, surrounded in turn by a deep envelope of molecular hydrogen and helium. This model had persisted for decades because it matched the limited gravity data available from the Voyager and Pioneer flybys, Juno's gravity measurements taken over many orbits with unprecedented precision told a different story. The variations in Jupiter's gravitational field at different latitudes and orientations could only be explained by a core that was not compact and well-defined, but diffuse, a region extending perhaps halfway to the surface where heavy elements, rock, ice, iron, silicates, were mixed throughout the surrounding hydrogen, their concentration declining gradually outward rather than ending at a sharp boundary. Jupiter's core was not a stone at the center of an ocean. It was more like a stain in the fabric of the planet, smeared outward by billions of years of convective stirring, perhaps still slowly spreading today. The Great Red Spot, that iconic storm larger than Earth's entire diameter, has been observed continuously since the 1830s and possibly as far back as the 1660s, when a 17th century astronomer named Giovanni Cassini described a persistent oval feature at similar latitude. The storm has been shrinking. In the early 19th century, it spanned perhaps 40,000 kilometers in its longest dimension, nearly 3 times Earth's diameter. By the time the Voyager spacecraft flew past in 1979, it had contracted to roughly twice Earth's width. Observations today show it at approximately 1.3 Earth diameters, around 16,400 kilometers across. Astronomers who have tracked this contraction wonder whether the storm will eventually dissipate entirely. whether it will stabilize at some minimum size maintained by the atmospheric dynamics of the surrounding jet streams, or whether its apparent shrinkage reflects a change in shape rather than in actual mass. The storm's perimeter has become more circular as it has contracted, and its internal wind speeds, which once reached 180 meters per second, have remained roughly constant even as its area has declined. When Juno passed within 9,000 kilometers of the Great Red Spot's cloud tops, closer than any spacecraft had previously come, the microwave radiometer revealed that the storm's roots extend approximately 300 kilometers below the visible clouds, far deeper than models had suggested. The base of the storm is warmer than the surrounding atmosphere at equivalent depths. This thermal anomaly drives an upward flow of air that feeds the anticyclonic circulation visible at the surface, a self-sustaining engine in which the warm base generates the updraft that maintains the rotation that generates the pressure gradient that keeps the warm air rising. The storm is not merely a surface phenomenon blown about by the winds. It is a deep, coherent structure with a thermal engine buried far below what any telescope has ever seen. Jupiter's magnetic field, unlike Earth's, which is broadly symmetric and well approximated by a simple bar magnet geometry, turned out to be dramatically different between its two hemispheres. The southern field was relatively smooth and regular, resembling a somewhat offset dipole. The northern field was complex and patchy, with concentrations of flux called magnetic flux patches that were inconsistent with any simple internal structure. The difference between north and south was more pronounced than anything seen in any other planetary magnetic field. What could cause such an asymmetry? Current hypotheses include a layer of stably stratified fluid near the top of the metallic hydrogen region that damps the dynamo differently in the two hemispheres, variations in the depth at which helium rain is occurring, or an interaction between the generating dynamo and the dilute core below. The magnetic field of Jupiter, it turns out, is a window into the deep interior, but it is a window that remains difficult to read. Among the more unexpected discoveries of the extended Juno mission was a phenomenon spotted in the upper atmosphere of Jupiter during a polar pass. The ultraviolet spectrograph captured a brief, intensely bright flash of ultraviolet emission in the high atmosphere, lasting only milliseconds, appearing without warning and vanishing completely before the instrument could track it. The spatial and temporal characteristics matched those of terrestrial sprites, the transient luminous events that appear above large thunderstorm systems when a powerful lightning discharge below drives a current upward through the stratosphere, briefly ionizing the thin air above the clouds into a bloom of light. On Earth, sprites appear red because the nitrogen molecules in the upper atmosphere emit red light when excited. On Jupiter, where hydrogen dominates, the spectral signature is shifted toward blue. The Juno observation marked the first detection of sprite-like events anywhere beyond Earth, confirming that this type of atmospheric electrical phenomenon is not unique to our planet, but may occur wherever powerful thunderstorms develop beneath a sufficiently deep atmosphere. The water abundance at Jupiter's equator also surprised mission scientists. The Galileo atmospheric probe, descending in 1995, found far less water than solar composition models predicted, less than 1/10 the amount expected if Jupiter formed from the same material as the Sun. This was puzzling, and for 2 decades it stood as an unexplained anomaly. Juno's microwave data showed that the probe had entered a hot spot, a locally dry descending region of the atmosphere that was profoundly unrepresentative of the planet as a whole. The northern equatorial belt, that wide brownish band visible in amateur telescopes, is genuinely dry, a region of sinking air that has been desiccated by its descent from higher altitudes. Elsewhere, water is present in quantities much closer to solar predictions. The Global picture is not uniform. However, Jupiter's atmosphere has a complex three-dimensional circulation, and the distribution of water within it reflects the details of that circulation in ways that are still being mapped. The cyclone systems at Jupiter's poles were another revelation. Previous missions had imaged the poles only obliquely from low latitudes, giving distorted views of the polar regions. Juno, in its polar orbit, photographed the north and south poles repeatedly and directly, revealing a geometry unlike anything seen elsewhere in the solar system. At the North Pole, 8 large cyclones are arrayed in a ring around a central 9th cyclone, each hundreds of kilometers in diameter, packed so tightly that their cloud systems intermingle at the edges. At the South Pole, the arrangement is 5 cyclones in a ring plus 1 at the center. These polygonal arrangements, an octagon in the north, a pentagon in the south, are stable structures that have persisted throughout Juno's mission without merging or dissipating, despite being in close contact with each other. The fluid dynamics that allow such systems to coexist stably without merging are a subject of active theoretical work, drawing on techniques from atmospheric physics, oceanography, and the study of geophysical fluid systems on Earth. Juno's extended mission, approved through 2025, shifted the spacecraft's focus outward. Rather than remaining in its original high polar orbit, the mission trajectory was redesigned to use gravitational interactions with Jupiter's large moons to reshape the orbit incrementally. This brought Juno into a series of close flybys. It was never originally designed for encounters with 3 of the 4 Galilean moons, the large satellites discovered by Galileo Galilei in January 1610. Galileo was not the only observer who may have seen these moons in those early weeks of 1610. The German astronomer Simon Marius claimed to have observed them independently, beginning perhaps a day earlier than Galileo. The priority dispute was never fully resolved in Marius's lifetime, and history assigned credit to Galileo, whose published account in the Sidereus Nuncius was clear, detailed, and supported by careful drawings of the moon's positions on successive nights. It was Marius who gave them the names we use today: Io, Europa, Ganymede, and Callisto, chosen from the mythology of Zeus, the Greek counterpart of the Roman Jupiter, on the suggestion of Johannes Kepler. Galileo himself preferred to call them the Medicean stars in honor of his patrons. Had that name prevailed, the Galilean satellites would have carried the surname of a Florentine banking family rather than the lovers and companions of a sky god. What Galileo grasped immediately was the significance of what he had found. 4 objects moving around Jupiter, not around Earth, not around the Sun, but around a third body entirely, in a universe where all celestial objects were supposed to circle either Earth or Sun. Here were 4 that circled neither. The geocentric model of the universe, which had dominated natural philosophy since Aristotle and been codified into the Ptolemaic system over the preceding 14 centuries, had a counterexample that anyone with a telescope could verify for themselves in a single clear night. Galileo's moons did not prove the heliocentric model, but they demolished a key argument against it, the claim that Earth must be central because it was the only body around which other bodies were known to orbit. Jupiter's satellites made that argument untenable. The largest of those 4 moons is Ganymede, and Ganymede is the largest moon in the entire solar system. Its diameter of 5,268 kilometers exceeds that of Mercury, the smallest planet, by nearly 500 kilometers. It is larger than Pluto by a factor of more than 2. It contains more water, mostly in ice form, than all of Earth's oceans combined. If Ganymede orbited the Sun directly, rather than Jupiter, it would be classified as a planet without hesitation. Instead, it orbits Jupiter at roughly 1 million kilometers from the planet's center, completing 1 revolution every 7 days and 3 hours. Its orbital period is fixed by the gravitational resonance it shares with its 2 inner neighbors, Europa and Io, a relationship so precisely maintained that the three moons will never align in a straight line, their positions cycling through a pattern that repeats exactly while never producing a triple conjunction. Ganymede is tidally locked, one face permanently toward Jupiter, the other permanently away. Standing on the Jupiter-facing hemisphere, the planet would dominate the sky, appearing nearly 5 times larger than the full moon appears from Earth, hanging motionless among the stars. From the far hemisphere, Jupiter would never be visible above the horizon, and the sky would be ruled by the 4.5 billion year progression of stars and the occasional passage of a neighboring moon. The difference in gravitational environment between the two hemispheres, one pulled constantly toward Jupiter, one facing outward, may produce subtle but detectable differences in geological structure, though separating these tidal effects from the other forces that have shaped Ganymede is a challenge that requires the kind of sustained orbital observation only JUICE can provide. The surface of Ganymede is immediately striking in its contrast. Roughly 40% of the terrain is ancient and dark, heavily cratered, preserving a record of the late heavy bombardment from the early solar system, when impactors were abundant and collisions frequent. The crater density in this dark terrain is comparable to that of the lunar highlands, among the highest anywhere in the solar system, suggesting a surface that has changed little in 4 billion years. The composition of this dark material includes complex organic compounds, organic compounds, hydrated silicates, and carbon dioxide ice, mixed into the water ice that forms the bulk of the surface. Its darkness is not absolute. It reflects perhaps 3 to 5% of incoming sunlight, making it roughly comparable to fresh asphalt, but against the bright grooved terrain that surrounds it. The contrast is immediately visible even in images taken from Earth orbit. The remaining 60% of the surface is younger and brighter, characterized by an extraordinary system of grooves, ridges, and troughs that cross-cut the older landscape in long, sweeping arcs. These groove systems are the most extensive tectonic structures on any icy moon in the solar system. Individual groove lanes extend for 1,000 kilometers. The ridges between them rise as high as 700 meters above the surrounding terrain, with slopes steep enough to trigger ice avalanches in the low gravity. In some regions, multiple generations of groove systems overprint each other, recording successive episodes of tectonic activity separated by geological intervals during which the surface was briefly quiescent. These structures record a period of intense tectonic activity early in Ganymede's history, during a phase when the moon's orbital parameters were still evolving toward the stable resonance configuration it currently occupies. As the orbit changed, the magnitude and timing of tidal forcing varied, driving the interior through cycles of increased and decreased heating. During peaks of tidal activity, the icy crust was fractured and stretched. Enormous plates shifted. Liquid water from the deep interior welled up through the fractures and refroze, resurfacing wide swaths of the older terrain with fresh ice. The bright material in the groove terrain is intrinsically more reflective than the ancient dark surface, partly because it is younger and has undergone less radiation darkening, and partly because the upwelling water deposited mineral-free ice that lacks the organic and silicate contaminants mixed into the older material. One of the most distinctive features in Ganymede's dark terrain is a crater chain called the Encke Catena, 13 overlapping impact craters stretching 161 kilometers across the surface in a nearly perfect line. The chain was formed when a comet passing too close to Ganymede was torn apart by tidal forces before impact. The comet's fragments continued traveling in formation along the original trajectory and struck the surface in rapid succession, each impact producing a crater whose size reflected the mass of the individual fragment. The systematic variation in crater size along the chain, larger craters toward the center, where the most massive fragments fell, tells us something about the size distribution within the comet's nucleus. The Enki Catena is a fossil record of a specific cosmic event that occurred sometime in Ganymede's past, preserved in the ancient dark terrain with the fidelity that only very cold and stable ice can maintain. Beneath the surface, Ganymede is differentiated into distinct compositional layers like a planet. At the center sits an iron and iron sulfide core, approximately 1,600 kilometers in diameter. Still partially molten, still warm from the combined effects of radiogenic heating, residual formation energy, and ongoing tidal friction. The temperature at the core exceeds 1,500 degrees Celsius, hot enough to keep the outer iron liquid and the inner iron solid, creating the conditions for a convective dynamo. Surrounding the core is a silicate mantle composed of material similar to ordinary chondrite meteorites, the most common type of stony meteorite that falls to Earth. Above the mantle lies the ice shell, nearly 900 kilometers thick, and within that shell, at a depth determined by the balance between internal heat and the freezing point of salty water at high pressure, there is a global ocean of liquid water. The evidence for this ocean is compelling and comes from multiple independent sources. Galileo's magnetometer detected oscillations in Ganymede's magnetic field synchronized precisely with Jupiter's 10-hour rotation period. As Jupiter's magnetosphere rocked back and forth, it induced electrical currents in Ganymede's interior, and the amplitude and phase of those induced currents were consistent with a conducting layer of a specific geometry and conductivity. Pure ice is not conductive. Rock is only marginally so. Salt water, on the other hand, conducts electricity readily, and the parameters derived from Galileo's data match those expected from a global layer of salty ocean, perhaps 100 kilometers deep. The JUICE mission, equipped with magnetometers 3 times more sensitive than Galileo's and capable of observing Ganymede from orbit over an extended period, will characterize this ocean layer in detail, measuring its depth, its thickness, its salinity, and the structure of the ice above it with a precision that Galileo, in its brief flybys, could not approach. What makes Ganymede unique among all the moons in the solar system is that it possesses its own intrinsic magnetic field, one generated internally rather than induced by an external source. This is extraordinary. No other moon anywhere, including Earth's own moon or any of the hundreds of moons around the other planets, is known to generate a magnetic field through internal processes. Ganymede's field is about 6 times weaker than Earth's, at equivalent distances from the generating source, but it is strong enough to create a miniature magnetosphere, a region of space around the Moon, where the local field dominates over Jupiter's background field, carving a bubble-shaped cavity in the surrounding Jovian magnetosphere. The boundary of this bubble, called the magnetopause, lies only a few hundred kilometers above the surface on the Jupiter-facing side, compressed by the dynamic pressure of Jupiter's rapidly sweeping field. On the anti-Jupiter side, it extends further, protected from direct contact with the Jovian field by the Moon's own magnetic pressure. This embedded magnetosphere produces one of the most visually distinctive phenomena associated with any moon aurorae at Ganymede's poles that rock back and forth in response to Jupiter's rotating field. As Jupiter's field changes orientation relative to Ganymede, the position of Ganymede's magnetopause oscillates, and the aurorae produced where energetic particles precipitate along field lines into the thin oxygen atmosphere shift latitudinally in response. The Hubble Space Telescope has observed these rocking aurorae and used the precise amplitude of their oscillation to constrain the properties of the conducting layer, driving the induced response, providing an independent ocean detection from the same data that the magnetometers measured in situ during Galileo's flybys. Ganymede's oxygen atmosphere, while far too thin to breathe, is rich in implications. Solar ultraviolet radiation breaks apart water molecules at the surface, releasing hydrogen and oxygen. The hydrogen, too light to be retained by Ganymede's weak surface gravity, escapes to space. The oxygen accumulates in both molecular and atomic form, producing the sparse exosphere that Hubble first detected in 1996. At the poles, where the geometry of the magnetic field channels particles down onto the surface with greater efficiency, the bombardment is more intense and the sublimation of surface ice more rapid. This drives a slow migration of water molecules from lower latitudes toward the poles, where they freeze out and accumulate as polar frost. The polar caps of Ganymede are thus not remnants of an ancient ice age, but actively maintained features, continuously replenished by the same high-energy bombardment that is simultaneously stripping mass from the Moon's atmosphere and driving chemistry in its surface ice. Europa is smaller than Ganymede by a factor of nearly 3,122 kilometers in diameter, slightly smaller than Earth's moon, the 14th largest object in the solar system. It orbits Jupiter at roughly 671,000 kilometers inside the intense radiation belts that make close approaches both scientifically valuable and technically demanding. Where Ganymede's ocean lies beneath nearly 150 kilometers of ice, Europa's ocean may be separated from space by only 15 to 25 kilometers of frozen crust, a relatively thin shell, and one that appears to be in active communication with the surface through fractures, upwellings, and possibly eruptions that spray ocean material directly into space. The surface of Europa is the smoothest in the solar system. This alone is diagnostically significant. A smooth surface is a young surface, one reshaped continuously by geological activity that erases craters as fast as they form. The few large impact craters that survive on Europa reveal something important. The largest impacts, which on a dead rocky or icy body would produce deep bowl-shaped excavations, instead show flat floors and relatively shallow profiles. This morphology, called multi-rearing structures or central pit craters, indicates that beneath a thin layer of cold, brittle ice, the underlying material was warm and slightly mobile at the time of impact. The impactor punched through the surface layer and encountered something below that was too warm to preserve the deep crater geometry expected in solid ice. That warm layer is almost certainly the ocean. Crisscrossing Europa's smooth surface is one of the most complex networks of linear features anywhere in the solar system. Long dark bands called lineae stretch for thousands of kilometers, some following great circle paths around the Moon as if ruled by the curvature of the globe. These bands were formed when the ice shell fractured and the two sides of the fracture moved apart, with fresh material welling up from below to fill the gap. A process analogous to seafloor spreading on Earth, though operating in a frozen medium and driven by tidal stresses rather than mantle convection. The dark reddish-brown color of the lineae is caused by material carried up from below salts, sulfur compounds, and possibly complex organic molecules that have been irradiated and chemically altered at the surface for millions of years. Broad regions called chaos terrain show where the ice shell has broken apart into angular rafts that have rotated, tilted, and refrozen in new positions, like a jigsaw puzzle disassembled and reassembled incorrectly. These regions may mark locations where a thermal plume rising from the ocean floor warmed the base of the ice sufficiently to cause partial melting, allowing the surface to fragment and drift before refreezing. In some cases, the fragments can be matched geometrically adjacent pieces that fit together when rotated back to their original orientations, demonstrating that the surface was truly mobile, not merely deformed. Connemara Chaos, one of the largest such regions on Europa, covers an area several times the size of Ireland and shows rafts of older, ridged terrain preserved as islands in a matrix of refrozen slush. The evidence for the ocean beneath Europa assembled gradually over decades from multiple independent lines of inquiry. Galileo's magnetometer detected a strong induced magnetic field, the same kind of conducting layer signature found at Ganymede, but stronger, implying a thinner ice shell and a more conductive ocean. Models of tidal heating applied to Europa's position in the Laplace resonance consistently predict that enough thermal energy flows through the Moon to maintain a deep global ocean indefinitely. And the surface geology, the youth of the surface, the lineae, the chaos terrain, the crater morphologies all require a liquid layer beneath the ice to explain their formation. No other model fits all the observations simultaneously. Water from Europa's interior has been detected in the space above the Moon. Observations using the Keck Observatory spectrograph, taken over 17 nights spread across several years, found the infrared signature of water vapor concentrated over a specific region of the Moon's trailing hemisphere. The quantity of vapor and its geographic concentration suggested an active eruption, a geyser reaching hundreds of kilometers into space, rather than diffuse sublimation of surface ice. Hubble Space Telescope images taken at ultraviolet wavelengths using the technique of transit spectroscopy as Europa passed in front of Jupiter's ultraviolet glow showed absorption features consistent with water vapor at the Moon's limb on multiple occasions, at positions suggesting plumes rising from specific geological features. These observations are at the edge of detectability, and the existence of sustained large plumes remains contested. But the detection of any erupted water vapor at all is significant. It implies that the ocean is communicating with the surface actively enough to reach space, and that a spacecraft flying through the right place at the right time could sample the ocean without touching the surface. The chemical environment of Europa's ocean has been studied extensively from the outside, using the composition of the surface material as a guide to what lies beneath. The reddish-brown coloring of the lineae and chaos terrain contains signatures of hydrated sulfates, salts formed when sulfur delivered to Europa's surface from Io's volcanic plumes via Jupiter's magnetosphere interacts with water. It may also contain magnesium sulfate, sodium sulfate, and chloride salts derived from the ocean itself. If the ocean's salinity is comparable to Earth's seawater, then the chemical environment available to potential organisms would include dissolved minerals, sulfur compounds as electron donors, and the oxidants produced at the surface, hydrogen peroxide, molecular oxygen, ozone, that are continuously being irradiated into the ice by Jupiter's particle environment. The challenge is getting those surface oxidants down into the ocean, where they could react with reduced compounds rising from the seafloor. If the ice shell is sufficiently active, if material cycles between surface and ocean on geological timescales, then that flux of oxidants may be sufficient to support a metabolically active biosphere in the dark water below. The deep oceans of Earth provide a template. Along the mid-ocean ridges where tectonic plates spread apart and hot mantle material rises to fill the gap, hydrothermal vents discharge superheated, mineral-rich water into the surrounding sea. The first such vent system was discovered in 1977 by scientists aboard the submersible Alvin, exploring the Galapagos Rift in the Pacific. What they found confounded expectations: a thriving ecosystem of remarkable density and diversity built around bacteria that extract energy not from sunlight but from the chemical energy released when reduced volcanic fluids rich in hydrogen sulfide, hydrogen, methane contact cold oxygenated seawater. Tube worms 2 meters long, white crabs, ghostly fish, dense mats of sulfur oxidizing bacteria, an entire food web sustained by chemistry alone, in complete darkness, at pressures that would crush unprotected human bodies. Later discoveries found ecosystems around different kinds of vents, cold seeps, serpentinization sites, lost city-type systems, where the reaction between seawater and olivine-rich rock produces hydrogen and methane, demonstrating that the template for life without sunlight is not one but many, varying with the local geochemistry, but united by the principle that wherever chemical energy is available in an aqueous environment, biology finds a way to exploit it. Europa's ocean floor is almost certainly in contact with its silicate interior. Tidal heating drives geological activity in that interior. The pressure at the bottom of Europa's ocean, perhaps 100 kilometers of water pressing down on the seafloor, is roughly 10 times the pressure at the deepest point of Earth's Mariana Trench. That pressure alone does not preclude life. Earth's most pressure-tolerant microorganisms, called piezophils, thrive at the bottom of that trench and show no signs of reaching a pressure limit. What matters biologically is the availability of chemical energy and liquid water. Europa appears to have both in abundance. NASA's Europa Clipper spacecraft, launched in October 2024, will arrive in the Jupiter system in April 2030, after a trajectory that uses gravitational assists from Mars and Earth. Over 3.5 years, it will conduct approximately 50 close flybys of Europa, each designed to cover a different part of the surface and a different altitude range. Its instrument suite includes a radar sounder to map the structure of the ice shell from the surface down toward the ocean boundary, a mass spectrometer to analyze the composition of any plume material encountered during low-altitude passes, a thermal emission imager to find warm regions in the ice that might mark geologically active zones, magnetometers to characterize the ocean through its induced magnetic field, and cameras ranging from wide-angle context imagers to high-resolution systems capable of resolving features smaller than a meter. One capability that emerged from laboratory research in preparation for the mission involves the night-side glow of Europa's ice. When high-energy electrons from Jupiter's radiation environment strike the icy surface, they excite atoms and molecules in the ice to higher energy states. As those states relax, they emit light, a faint greenish luminescence called electron-stimulated luminescence. The spectral character of this glow depends on the composition of the ice. Pure water ice glows differently from ice contaminated with salts or sulfur compounds. Europa Clipper's cameras, sensitive enough to detect this faint emission, may be able to map the chemical composition of the surface by photographing the night side, reading the chemistry of the ice by the color of its radiation-induced glow, and using that chemistry to trace the connection between surface material and the ocean below. The surface of Europa conceals another hazard for any future landing mission. Across the equatorial and mid-latitude regions, modeling suggests the existence of large ice formations produced by differential sublimation, tall blade-like structures called penitentes, known on Earth from the high-altitude dry deserts of the Andes, where they reach heights of a few meters. On Europa, the conditions for penitent formation are extreme: intense radiation-driven sublimation, no atmospheric erosion, extremely low temperatures, and geological timescales of formation. Calculations suggest that Europa's penitentes could reach 15 meters in height, spaced roughly 7 meters apart, covering large portions of the equatorial surface in a field of frozen blades as tall as a 5-story building. A lander descending into such terrain without prior centimeter-scale surface mapping would face hazards for which no existing spacecraft design is prepared. Io is a different kind of world entirely, a world of fire rather than ice, of geological violence rather than frozen stillness. It orbits Jupiter at 421,700 kilometers from the planet's center, well within the most intense portions of the radiation belts, and it is the most volcanically active body in the solar system. Not just more active than any other moon, more active than Earth by a significant margin per unit surface area. More than 400 distinct volcanic centers have been identified on its surface, and at any given time, dozens are erupting simultaneously. The surface of Io has been completely resurfaced by volcanic deposits in the geological recent past, perhaps within the last million years. There are no ancient craters, no primordial terrain. Io has been continuously overprinted by its own geology, burying the record of its early history under kilometers of accumulated lava and sulfurous frost, The volcanism of Io was predicted before it was observed, in one of the more remarkable instances of theoretical success in planetary science. In late February 1979, just days before the Voyager 1 spacecraft reached the Jovian system, a planetary scientist named Stanton Peale and two colleagues published a paper in the journal Science. Working through the mathematics of tidal dissipation in a body locked into the Laplace resonance with Europa and Ganymede, they calculated that the tidal heating rate in Io should be approximately 100 times greater than Earth's radiogenic heat production, enough to produce intense global volcanism. The paper was published on March 2, 1979. Voyager 1's closest approach to Io occurred on March 5th. 3 days later, a mission scientist named Linda Morabito noticed, while processing a navigation image, a faint umbrella-shaped plume rising 280 kilometers above Io's limb. By the time Voyager 1 left the Jovian system, 8 active plumes had been identified. Peale's prediction had been confirmed within days of its publication by data that was already in transit when his paper appeared in print. The mechanism driving Io's volcanism is tidal friction, continuously applied. As Io orbits Jupiter, the gravitational field of the planet, combined with smaller but non-negligible perturbations from Europa and Ganymede in their resonant orbits, deforms Io's shape in a rhythmic pattern. The satellite is not perfectly spherical even at rest. Tidal forces stretch it along the Jupiter-facing direction. But because Io's orbit is slightly elliptical, its distance from Jupiter varies and the magnitude of the tidal distortion varies with it. The surface rises and falls by as much as 100 meters during each 42-hour orbit. This mechanical flexing generates heat through friction between slightly different layers of the interior that want to deform at slightly different rates. The energy dissipated in Io by this mechanism is enormous, roughly 100 terawatts, approximately equivalent to the total power output of all human energy use on Earth. This energy cannot build up indefinitely, it must be released. Io releases it through its volcanoes. The volcanic features on Io are diverse and in some cases unlike anything on Earth. The dominant low-lying volcanic structures are paterae, broad, shallow calderas with flat floors and steep walls, sometimes hundreds of kilometers in diameter. Loki Patera, the largest, is a lava lake roughly 200 kilometers across with a surface that periodically overturns as dense solidified crust sinks and fresh magma wells up from below. This overturning has been observed from Earth in thermal infrared, progressing around the Patera in a wave at a measurable rate, confirming the lava lake interpretation. Pele, another major volcanic center, produces a persistent plume of sulfur dioxide and sulfur vapor that deposits a distinctive reddish ring of sulfur on the surrounding terrain visible from Earth. The Tefestar Paterae complex near Io's North Pole produced one of the most dramatic volcanic events ever observed on another world, a curtain of fire photographed by the New Horizons spacecraft in 2007, with lava fountains reaching 50 kilometers above the surface. The largest structures on Io's surface are not volcanic calderas but mountains, compressional ridges and isolated peaks thrust up by the same tectonic forces that also drive the volcanism. As lava continuously deposits new material on the surface, the crust below is buried and compressed, generating horizontal stress that buckles the lithosphere upward in places. The mountains of Io are not built by addition of material from above, like Earth's volcanic mountains, but by compression from below, folded and thrusted into prominence by the inexorable accumulation of new volcanic deposits elsewhere. Some of these mountains exceed the height of Everest. Khazau Le Montes rises approximately 18 kilometers above the surrounding plains, making it one of the tallest peaks in the solar system. Io's mountains are enormous, isolated and surrounded by low volcanic plains, an alien landscape that has no counterpart elsewhere. The surface composition of Io is dominated by sulfur dioxide frost, which covers most of the terrain in white and yellow deposits. but underlying these sulfurous materials are silicate lavas, the signature of high-temperature magmatic activity that resembles in some respect the komatitic volcanism of Archean Earth more than 3 billion years ago. Eruption temperatures inferred from the thermal emission of Io's volcanic hotspots are extraordinarily high. Some events have been estimated at temperatures exceeding 1,600 degrees Celsius, approaching or exceeding the temperature of the hottest lavas on modern Earth and suggesting a composition closer to pure pyroxene or even ultramafic peridotite than to ordinary basalt. If correct, Io is preserving a style of volcanism that Earth itself abandoned when its mantle cooled enough to prevent the generation of such high-temperature melts. The interaction between Io and Jupiter's magnetic field constitutes one of the most powerful natural electrical circuits known to planetary science. As Jupiter's magnetic field rotates past Io faster than Io orbits, because Jupiter's magnetosphere corrotates with the planet's 10-hour spin, it sweeps through Io's ionized atmosphere, inducing an electromotive force across the Moon. This drives an electrical current along the magnetic field lines connecting Io to Jupiter's polar ionosphere, a flux tube carrying an estimated 5 million amperes at voltages of roughly 400,000 volts, with a total power delivery of approximately 2 terawatts. Where this current arrives at Jupiter's ionosphere, it produces a bright ultraviolet spot in the polar aurora, the Io footprint, visible in Hubble Space Telescope images as a distinct bright knot moving through the main auroral oval at Io's orbital period. Trailing behind the primary spot are secondary and tertiary footprints, reflections of the current that has bounced back and forth along the flux tube. The material that Io continuously injects into Jupiter's magnetosphere feeds a dense plasma torus, a donut-shaped cloud of ionized gas that encircles Jupiter along Io's orbital path. This torus glows in the ultraviolet and optical, visible in specialized ground-based images as a faint luminous ring. It is the dominant source of heavy ions, sulfur, oxygen, sodium, potassium in the Jovian magnetosphere, and its properties determine much of the radiation environment experienced by the outer moons. Europa and Ganymede are bombarded by ions that originate in Io's volcanoes, travel through the torus, and are accelerated to high energies in Jupiter's radiation belts before striking the icy surfaces of the outer moons. In this sense, Io does not just inhabit the Jovian system. It shapes the environment in which Europa's surface chemistry and Ganymede's ionosphere operate. Beyond Ganymede, at the outer edge of the Galilean family, orbits Callisto, a world almost as large as Ganymede but profoundly different in character. Callisto's diameter of 4,820 kilometers makes it the third largest moon in the solar system, and its surface is the most cratered of any body yet photographed in detail. Unlike its 3 inner siblings, Callisto shows no evidence of internal geological activity at any point in its history. There are no grooves, no chaos terrain, no signs of tectonic disruption. The surface it presents to our instruments is essentially the same surface it has had for 4 billion years, an undisturbed record of every impact it has suffered since the heavy bombardment ended. The reason for this difference lies in Callisto's position outside the resonance. With no tidal interaction to heat its interior, Callisto never differentiated fully. Rock and ice were never separated into distinct layers. The interior remained cold and mixed. The ice never melted enough to allow the dense rocky material to sink toward the core. Callisto is in some sense a fossil of the early solar system, a body that formed in the outer Jovian system, accumulated its material, and then simply stopped evolving. And yet Callisto too may harbor an ocean. Galileo's induced magnetic field measurements show the conducting layer at Callisto as well. Weaker than Europa's signal, more ambiguous but present. The challenge is explaining how Callisto, with its undifferentiated interior and no tidal heating, could maintain liquid water? The answer probably involves ammonia. If a few percent of ammonia is mixed into Callisto's ice, it lowers the melting point significantly, potentially enough to maintain a liquid layer at the temperatures achievable by radiogenic heating alone without any tidal contribution. A cold, ammoniated ocean, possibly far below the surface, in a body that otherwise looks geologically dead. It is one of the more counterintuitive possibilities in solar system science. To understand Jupiter itself, the planet whose gravity holds all of this in place requires descending into it, at least conceptually. The visible cloud tops are a deceptively thin veil over a planet that extends 70,000 kilometers to its center. What lies beneath is accessible only through inference and remote sensing mediated by physics explored in terrestrial laboratories at the pressure and temperature extremes relevant to planetary interiors. The atmosphere of Jupiter, viewed from above, is organized into alternating light and dark bands. The light bands, called zones, are regions of rising air that expand laterally and cool, producing ammonia ice crystals that reflect sunlight and give the zones their pale appearance. The dark bands, called belts, are regions of sinking air, drier and warmer, showing the deeper, darker haze layers beneath. The boundary between zones and belts is maintained by eastward and westward jet streams, whose speeds reach 150 meters per second, faster than any sustained winds measured at Earth's surface. These jet streams have been present at approximately the same latitudes throughout the entire period of telescopic observation, which spans more than 3 centuries. They are not transient weather systems, but a permanent feature of Jupiter's atmospheric circulation. The energy driving this circulation comes primarily from Jupiter's interior. Unlike Earth, which receives most of its atmospheric energy from the Sun and radiates approximately as much energy as it absorbs, Jupiter emits roughly 1.7 times more energy than it receives from the Sun. The excess comes from the slow gravitational contraction of the planet over billions of years and from the sinking of helium droplets through the metallic hydrogen interior, a process called helium rain that converts gravitational potential energy into heat. This internal heat source drives a deep convective circulation throughout the molecular envelope that extends from the cloud tops downward through tens of thousands of kilometers, carrying heat toward the surface and generating the jet stream structure visible at the cloud tops. The Galileo atmospheric probe descending in December 1995 experienced these jets directly. As it fell from roughly 600 kilometers above the visible cloud tops to its termination point 160 kilometers below them, it measured winds that increased with depth. Near the ammonia cloud layer at the top of the descent, winds were already blowing at roughly 100 meters per second. Deeper, they reached 170 meters per second and showed no sign of decreasing as the probe approached its destruction. This was the first direct evidence that Jupiter's jet streams are not shallow atmospheric phenomena driven by surface absorption of sunlight, as analogous features on Earth are, but deep structures that extend well below the cloud layers, driven by heat rising from the planetary interior. The transition from Jupiter's molecular atmosphere to its metallic interior is not a sharp phase boundary, but a gradual change that occurs somewhere between 15,000 and 20,000 kilometers below the cloud tops, where pressure exceeds 1 million atmospheres and temperature exceeds 10,000 degrees Celsius. At these conditions, hydrogen, which is normally a molecule of 2 protons and 2 electrons bonded together, begins to ionize. The electrons detach from their parent protons and become free to move through the fluid independently. As the fraction of free electrons increases, the fluid's electrical conductivity increases, and it acquires the property that defines a metal, the ability to conduct electricity. The transition is continuous, the fluid never solidifying, the conductivity increasing smoothly over a range of pressures rather than jumping at a specific threshold. The term metallic hydrogen, while evocative describes a state more like a high-pressure, high-temperature conducting plasma than anything we associate with metals in everyday experience. Within this metallic hydrogen layer, convective motion of the conducting fluid generates Jupiter's magnetic field through the dynamo process. The field produced is enormous. The planet's magnetic dipole moment is roughly 20,000 times Earth's, but as Juno showed, it is not a simple dipole. The complexity of the field, with its different character in the two hemispheres and its multiple high-order components, reflects the structure of the flow within the generating layer. Where convection is strong and organized, the field is coherent. Where it is complex or disrupted, the field shows structure at smaller spatial scales. Mapping the field precisely over many orbits is equivalent to imaging the interior circulation, a form of magnetic tomography that reveals what direct observation cannot. Deep in the interior, below the dynamo-generating layer, in the region that Juno's gravity measurements identified as the dilute core, conditions approach the most extreme accessible to theoretical calculation. Pressures of tens of millions of atmospheres, temperatures of 20,000 to 40,000 degrees Celsius. Under these conditions, the distinction between rock, ice, and metallic hydrogen becomes blurred. Heavy elements, oxygen, carbon, silicon, iron, magnesium, are dissolved in the metallic hydrogen in concentrations that decline gradually outward. The boundary of this dilute core, if it can be called a boundary, is not a sharp interface, but a region where the concentration of heavy elements decreases from a central maximum to the background level of the outer envelope. Whether this structure formed during Jupiter's initial assembly as a large rocky core was built up by the accretion of planetesimals before the onset of rapid gas accretion, or whether it evolved subsequently through the erosion and mixing of a once compact core, remains one of the central unresolved questions in planetary science. Jupiter formed earlier than any other planet for which isotopic constraints are available. Iron meteorites, which preserve the chemical signature of their parent asteroid's cores, can be sorted into distinct groups based on their isotopic composition. These groups were isolated from each other during the first few million years of the solar system's history, suggesting that a barrier to the exchange of material between the inner and outer solar system appeared early and persisted. That barrier was almost certainly Jupiter's growing core, which opened a gap in the protoplanetary disk as it grew massive enough to gravitationally perturb the surrounding material. A core massive enough to open a disk gap must have reached roughly 10 to 20 Earth masses within the first million years of the solar system's history, making Jupiter's core the first large solid body to assemble in the solar system. The consequences of this early formation were profound. Jupiter's gravity, enormous from an early date, shaped the architecture of everything that followed. It scattered material from the outer solar system inward, delivering water and organic molecules to the terrestrial planets. It deflected planetesimals that might otherwise have coalesced into a larger mass, which is only about 1/10 of Earth's mass, far smaller than models of rocky planet accretion would predict in the absence of a large outer perturber. It established the outer solar system's resonance structure, corralling the ice giants and eventually the Kuiper belt into configurations that had been broadly stable for billions of years. And it created the conditions, the thermal gradient across the protoplanetary disk, the delivery of volatile materials from the outer system, the perturbation of impact rates across the inner planets, under which life emerged on at least one world. The 4 Galilean moons each bear the signature of their formation in Jupiter's thermal shadow. Io, closest to the warm young planet, formed too hot for ice to condense, so it accumulated almost entirely from silicates and iron, giving it the high density of a rocky planet and the complete absence of surface water. Europa, slightly farther, formed near the snowline, capturing a thin veneer of water over a rocky interior, enough for a global ocean, not enough to make it primarily icy. Ganymede and Callisto, farther still, formed where ice was abundant and were built in roughly equal proportions of rock and ice. This gradient, from dry fire world to deep ice ocean to frozen desert, is not random. It is a map of temperature written in composition, preserved in the structures of 4 worlds that have orbited unchanged in their relative proportions since the earliest days of the solar system. The ocean on Europa has had 4.5 billion years to develop chemistry. The ocean on Ganymede has had the same. These are not brief experiments in aqueous chemistry. They are the longest-running liquid water environments in the solar system, older than Earth's oldest surviving rocks, older than the first unambiguous microbial fossils in the geological record, older than the earliest evidence of photosynthesis. If life can arise in liquid water, given sufficient time and a supply of chemical energy, then the moons of Jupiter have had more of both than Earth had when life first appeared here. We have sent 9 spacecraft to the Jovian system over 5 decades. Pioneer 10 and 11, Voyager 1 and 2, Ulysses, Cassini, New Horizons, Galileo, and Juno. Each mission has returned data that changed what we thought we knew. Pioneer found the radiation belts were more intense than expected. Voyager found active volcanoes on Io, complex surface geology on Europa and Ganymede, and the ring system around Jupiter. Galileo found the induced magnetic field signatures of subsurface oceans at Europa, Ganymede, and Callisto, and watched the impact of comet Shoemaker-Levy 9 on Jupiter in 1994. Juno found the dilute core, the asymmetric magnetic field, the deep roots of the Great Red Spot, and the rocking polar aurorae. Each successive mission has found Jupiter's system more complex, more dynamic, and more interesting than the previous one had suggested. The next missions carry the ambition that this complexity warrants. JUICE, the Jupiter Icy Moons Explorer, will spend years in the Jovian system conducting the first sustained orbital study of a moon other than Earth's own. Europa Clipper will perform the most comprehensive reconnaissance of a potentially habitable ocean world ever attempted. Future missions, still in early planning phases, aim at the surface of Europa and ultimately at the ocean beneath, drilling through the ice, releasing a submersible, and exploring a body of water that no sunlight has touched since the solar system was young. What they will find, we cannot predict. Planetary science has been wrong enough times about worlds that turned out to be more interesting than expected that any specific prediction invites humility. What we can say is this: the Jovian system is the most concentrated collection of scientifically significant targets accessible to spacecraft in the near future. 3 ocean worlds, a volcanic world unique in the solar system and the largest planet we know, each raising questions fundamental to our understanding of how planets work, how chemistry organizes itself in liquid water, and whether the conditions we associate with life on Earth are common or rare in the universe. If those conditions are common, and the moons of Jupiter are our best nearby test of that hypothesis, then the implications extend far beyond this particular system, to every ocean world orbiting every gas giant around every star we have ever observed. The question we are asking at Jupiter is not a local question. It is the question of whether we are alone posed to the nearest available audience. Somewhere below the surface of Europa, water moves in darkness that has lasted for geological epochs. Whether anything moves within that water, whether any chemistry has organized itself into the specific kind of complexity we call life, we do not yet know, but we are going to find out. The spacecraft are already on their way. The question of how life arises is not fully understood even on Earth, where we have a complete example in front of us. What we know is that life here appeared remarkably quickly. The earliest evidence of microbial activity in the geological record dates to roughly 3.7 billion years ago, within a few hundred million years of the end of the heavy bombardment period, when impactors were still common enough to sterilize the surface periodically and the oceans were still relatively young. Life did not wait for the solar system to become quiet. It appeared as soon as conditions permitted, which tells us either that life arises with high probability whenever suitable conditions exist, or that the window of conditions required is broader than our experience on a single world allows us to determine. The moons of Jupiter will not resolve that ambiguity by themselves, but they will add data points, the most valuable data points available to us outside Earth's own biosphere. There is a subtler reason why Jupiter's system matters beyond the direct search for life. The ocean worlds of the outer solar system are connected to their environments in ways that inner system planets are not. Europa's surface chemistry is dominated by material bombarded in from Io via Jupiter's radiation belts. Ganymede's atmosphere is maintained by the energy delivered by the same radiation environment. The plasma torus fed by Io's volcanism determines the flux of ions that strike Europa's ice and produce the oxidants that may fuel any life in the ocean below. The Jovian system is not a collection of isolated worlds, but an ecosystem in the broadest physical sense, a network of material and energy flows connecting bodies that are millions of kilometers apart, linked by magnetic fields, plasma currents, gravitational resonances, and the relentless energy output of the planet at the center. Understanding any one body in this system requires understanding the system as a whole. This is why missions to Jupiter are not simply excursions to interesting destinations. They are studies of a complex environment whose components cannot be understood in isolation. The Juno mission, in its extended phase, became a mission to that whole system rather than to Jupiter alone. Each flyby of a Galilean moon added context. The plasma environment around Io, the ice composition at Ganymede, the induced field measurement at Europa. Juno's instruments were not designed for these encounters. They were designed for Jupiter itself, but their sensitivity was sufficient to extract scientific value from brief close passages. The magnetometer sweeping through the space around Ganymede measured the field with enough precision to constrain the ocean's conductivity. The microwave radiometer pointed at Io during one flyby detected thermal emission from volcanic hotspots beneath the sulfurous crust. UNOCAM captured images of Ganymede's grooved terrain at resolutions comparable to the best Galileo achieved, and returned images of Io's volcanic plains that revealed new eruptive features not previously catalogued. What UNO could not do, and what JUICE and Europa Clipper are designed to accomplish, is observe any of these moons over time, building up a record of geological and atmospheric change across multiple orbits, tracking how the system evolves. A single flyby is a snapshot. Sustained orbital observation is a film. The difference is the difference between describing a living system and understanding it, between seeing a moment in the life of a world and following the processes that created it, that sustain it, and that will eventually transform it into something different. The science of the Jovian system has reached the stage where snapshots are no longer sufficient. The next decade's missions will provide the film. The history of outer solar system exploration is a history of surprises that, in retrospect, all follow from the same underlying principle. Liquid water is not rare. In 1977, before Voyager had reached the outer planets, the prevailing assumption was that the giant planets' moons would be geologically dead, cold, ancient, cratered, inert. Voyager 1's discovery of Io's volcanoes destroyed that assumption for the innermost Galilean moon. The Galileo mission's detection of induced magnetic fields at Europa, Ganymede, and Callisto destroyed it for the rest of the Galilean family. The Cassini mission orbiting Saturn from 2004 to 2017 found a geyser-active ocean world at Enceladus, a moon barely 500 kilometers across, small enough to fit comfortably within the borders of France, erupting a plume of water vapor and ice particles that supplies material to Saturn's E-ring and has been found to contain hydrogen, complex organic molecules, and silica nanoparticles that indicate active hydrothermal chemistry at the ocean floor. The New Horizons mission, passing Pluto in 2015, found a geologically active dwarf planet with mountains of water ice, a nitrogen glacier, and atmospheric hazes produced by photochemical reactions occurring in the thin nitrogen methane atmosphere. Every world we have visited has turned out to be more active, more complex, and more chemically interesting than we expected before we arrived. This pattern, the pattern of consistently underestimating the geological and chemical vitality of icy worlds, is itself scientifically significant. It tells us something about the physics of icy bodies. That water ice is a remarkably effective medium for maintaining internal heat, that tidal forces and radiogenic heating are more widespread and powerful than early models assumed, and that the conditions required for liquid water are far less restrictive than they appeared when Earth's oceans were the only example we had. The solar system, once thought to be a collection of a few warm rocky worlds surrounded by frozen wastelands, is now revealed as a system in which liquid water, and therefore the potential for aqueous chemistry of the kind we associate with life, is distributed widely, maintained by diverse energy sources, and preserved for geological timescales at numerous locations far from the Sun. Europa and Ganymede are not anomalies in this picture. They are examples of what appears to be a common phenomenon: ocean worlds, maintained by tidal and radiogenic heating, distributed throughout the outer solar system and probably throughout planetary systems around other stars. Every gas giant that has been observed around other stars may harbor moon systems. Those moon systems, if they are anything like Jupiter's, may contain ocean worlds of their own. The search for life beyond Earth is not confined to the habitable zones of other stars, the narrow annular regions where surface water could exist on a rocky planet. It extends to the moons of gas giants throughout the galaxy, wherever tidal forces are strong enough and chemistry is rich enough to maintain liquid water in the dark beneath the ice. What we will learn at Europa and Ganymede in the coming decades will not be the end of this search. It will be the beginning of understanding whether what we find there, life or its chemical precursors, or simply the conditions that make it possible, is a local accident of the Jovian system's particular configuration, or an expression of something more general, more widespread, and more fundamental about the way matter organizes itself in liquid water over geological time. That is the question hanging over every flyby, every radar measurement, every magnetometer reading, every infrared spectrum returned from this extraordinary collection of frozen worlds. It is the deepest question in planetary science, and possibly in science altogether. The story of how we came to understand that Jupiter's moons might harbor life is also the story of how we learned to think differently about what life requires. The assumption that dominated planetary science for most of the 20th century was that life needed sunlight, that photosynthesis was the only viable energy pathway for building a biosphere complex enough to sustain itself, and that therefore only planets in the narrow habitable zone around their parent star could support biology. This assumption was not unreasonable given the evidence available. Every ecosystem on Earth's surface, however different in composition and structure, ultimately traced its energy back to the Sun through photosynthesis at its base. Life, on the evidence of the only example we had, was a solar-powered phenomenon. The discovery of hydrothermal vent ecosystems in 1977 changed this understanding permanently and at a stroke. When the submersible Alvin descended to the Galapagos Rift and found dense communities of organisms, including species entirely new to science, living in complete darkness at the bottom of the Pacific, the conceptual framework for astrobiology had to be rebuilt from fundamentals. Sunlight was not the only energy source capable of sustaining a biosphere. Chemical energy, specifically the energy released by oxidation-reduction reactions involving volcanic gases, could do it too. And if it could do it at one hydrothermal system on Earth's ocean floor, it could do it at any hydrothermal system on any ocean floor, in any ocean that was in contact with a geologically active rocky interior, anywhere in the universe that tidal or radiogenic heating maintained liquid water. The theoretical chain from this realization to the question of life at Europa is short and direct. Europa's ocean is in contact with a rocky seafloor. That seafloor is heated by tidal forces. Tidal heating drives geological activity. Geological activity, faulting, fracturing, magmatic intrusion drives hydrothermal circulation. Hydrothermal circulation carries reduced compounds, hydrogen sulfide, methane, from the rocky interior into the ocean. If oxidants from the surface, hydrogen peroxide and oxygen produced by radiation, cycle down through the ice and into the ocean over geological time, then reducing and oxidizing compounds meet in the water column and generate a chemical energy gradient. A chemical energy gradient in liquid water, maintained for billions of years, is everything life needs. Whether life has appeared to exploit it is the only remaining question, and it is not a question we can answer from Earth. Every instrument aboard Europa Clipper, every orbit JUICE will fly around Ganymede, every close pass Juno made through the Jovian system. All of it serves, ultimately, the same purpose. Not merely to describe these worlds in their physical detail, though that description is itself valuable. Not merely to advance our understanding of planetary formation and evolution, though that advance is already substantial. The deeper purpose is to determine whether what we call life, that specific and extraordinary organization of matter that sustains itself against thermodynamic equilibrium, reproduces and evolves, is a phenomenon unique to Earth or common in the universe. The moons of Jupiter are the nearest laboratory in which that question can be addressed. They are the first and closest test of whether life, as we know it, is the peculiar outcome of one improbable accident 4 billion years ago, or the natural tendency of chemistry in water given time enough and energy enough to find its way.